gravity is pairwise between every possible pair of objects. But unless the mass is very large, all these forces are very much weaker than friction. Like all the other kinds of interactions are simply just way stronger than gravity. So all other interactions like gravity and not gravity, excuse me, like friction, air resistance, normal forces, just yeah. So you can see that even though gravity is very simple, because it's pairwise, and there are lots and lots of different objects to consider gravity playing a part in its motion and interactions, thinking about nature can quickly become overwhelmingly complicated because everything interacts with every other thing via gravity. But the thing is unless the mass is very large, like the moon and the earth together, all of these forces are very much weaker than all the other interactions. So the forces between apples, you don't have to think about them. They are much bigger forces involved in influencing the apple's motion. The gravitational force between people standing next to each other, neither of these people is ever going to feel that. We don't have sensory perception that's that fine, first of all. Second of all, the air resistance that you feel on your skin is way stronger than any gravitational interaction with another person or an automobile or even an entire building that you stand next to in a downtown area. Yeah, so good. So kind of gets crazy, but really you just want to pay attention to the big objects. So if Earth is involved, Earth is the big object, and even with small objects like this apple, the apple and the Earth have an interaction that's strong enough to cause the apple's motion to change a lot, possibly. And that's really the point. Okay, so the universal law of gravity, it gets written this way. The force involved in a gravitational interaction is proportional to the product of the two masses involved. So here is object A, and here is object B. And this has mass A, and this has mass, B. So these are the amounts of material for each of these objects. The force is proportional to mass of A times the mass of B. And it doesn't matter who's A and who's B. This is, right, the product is commutative, so you can switch the order, it doesn't matter. And force is inversely proportional to the distance between centers. I'll put centers in quotes. It's the distance between the centers squared. So this is the reason why gravity is referred to as an inverse square law force. Inverse square law force. So that's what it's called. So that distance between the two centers squared, here's the distance. It is from essentially about here, right? That's the distance between the centers. So let's go over to here, like this. And so we can write that F goes like ma times mb divided by d squared, where this symbol means goes like. So the way we can get equals, though, right? If we want a law of gravity that calculates things for us, it tells us what the value is, we need to be able to write down equal signs. And so if it goes like this, maybe there is a constant of proportionality such that we can use the stronger equal sign this way. And in SI units, G, think about what G needs to do. G needs to multiply on kilograms times kilograms, that's the SI unit of mass, and it also needs to get divided by meters squared and give us newtons. So G needs to be meters squared per kilogram squared with newtons. So this is what G does. G needs to take in meters squared on the bottom and kilograms squared on the top. You can see they're reversed here in G, and then spit back force, SI units of force. And it turns out that you can go and measure G equals about 6.67 times 10 to the minus 11. So this is small, newtons meters squared per kilogram squared. And because of the 10 to the minus 11, gravity is considered weak. It is not very strong, even though it is the force that essentially controls the shape of galaxies and holds the entire mass of the moon in orbit around the Earth, for example. And it's the thing that sticks together the solar system, right? That's gigantic. It's the thing that holds the ocean to the Earth, right? The ocean's really heavy. So it's crazy to refer to this as a weak force, but gravity is, it turns out, compared to the other interactions in nature, gravity is extremely weak. Okay, so continuing with conceptual introduction, orbits. So orbits come in two types. There is a really interesting possible orbit called a circular orbit, and then another type of orbit which tends to be actually how things orbit. It's elliptical. A circular orbit is quite hard to have, but theoretically it is possible. An elliptical orbit is, in some sense, a sloppy circular orbit. And then there is something else that gravity does, and it's called hyperbolic trajectory. And I think it's important to point out that this is not an orbit. So let me draw you some pictures of this conceptual thing. So here is the Earth, and there can be a satellite of the Earth in circular motion. So this satellite if it goes in circular motion, that means it stays the same distance away. So this is a little satellite. And it's going around and right. Okay, so that's a circular orbit. Another type of orbit is an elliptical orbit. An elliptical orbit looks like this instead. So here's an example of an elliptical orbit that actually gets a little close to the Earth compared to the circular orbit. Here it is. So this is the point of closest approach, and then all it does is get further away, goes out to some far point, and then turns around and falls all the way back down, and then gets back to that point of closest approach and does it again. So this is an elliptical orbit. For example, this is what the moon does around the Earth. It's not as extreme as this. The moon's orbit is quite a bit more circular than what this looks like. So in this drawing, it's pretty neat to point out that if this is the center of the Earth and this is the moon, this distance on the long side is called the aphelion. This is the distance of furthest approach, and then the distance of closest approach is called the perihelion, or the perihelion. In an elliptical orbit, there's some special places. One of the places, or actually both places, are referred to as foci. These are foci of the ellipse. And they're geometrically interesting. So the other focus is sort of symmetrically over here. So foci of the ellipse, they are geometrically interesting. You can go and Google this if you'd like. It's pretty cool construction. Ellipses are very special. Circular orbits, the aphelion and the perihelion are the same value. And in fact, a circle is an orbit where both foci sit at the same place. So circle orbits have the two ellipse foci. They just happen to be at the same place, and the aphelion and perihelion distances just have the same value. A hyperbolic trajectory is the situation of an object that comes in from far away. So here it is. And it's not headed towards the Earth. If it was headed towards the Earth, all it would do is run into the Earth. And I guess there's a sense in which that's a hyperbolic trajectory, but it's not interesting. So I'm going to give this incoming object that's coming in from very, very far away a velocity out here that's on its way to missing the Earth. But because it's attracted to the Earth as it falls, it's going to bend, its trajectory bends towards the Earth. So here it comes. Now it's becoming kind of drawn to the Earth. And then, though, it just keeps on going. And in the long time limit, it's just going in a straight line far away from the Earth again. And this is called the hyperbola. And this hyperbola does also have a distance of closest approach as well. Yeah, so these are the three types of things that gravity does in the astronomy scale.